All right, everyone, we're back. And next talk is going to be about WASI Web GPU and graphics stuff by Mendy Berger. So please welcome Mendy.
I'm Mendy Berger. I work at Redmond, and I'm focusing on WASI Web GPU. I'm a little nervous, so please bear with me, but we'll manage. So let's jump into it. First question is, why WASI Web GPU in the first place? So we all here are fans of WASM. WASM provides secure sandboxing for code on the CPU, and it also runs across platforms, so you can use it for portability as well. But that works great for CPUs, but what about GPUs? So Web GPU can be the answer to that. Web GPU already works in the browser, so it's a widely supported standard. And you can even use it outside the browser, so it's not secure. So it's a widely secure standard already, and works already. It's quite secure. What are some use cases for it? So obviously, just graphical UI applications you can build with WASI Web GPU, but you can also do things like headless graphics, rendering plugins if you want to give maybe a small window in your application to a plugin. You can do that with WASI Web GPU. You can virtualize GPU resources. And use it for arbitrary GPU compute, like physics simulation and stuff. And you can even use it for AI, or maybe things that aren't covered by WASI-NN. WASI-NN, I believe, focuses mostly on inferencing. And what about training, maybe tuning, or maybe a backend that yet? Since WASI Web GPU is a little more generalized, you should be able to build it on top of WASI Web GPU. So before we go into the actual architecture of WASI Web GPU, let's just look at a few examples and of it running, just to see like what's possible. So we have a graphical application that runs in WASI Web. Fancy, but you can see Cybertruck moving around with my mouse. So you can build the graphical application with WASI now. And this is an AI example. It's going to try to infer what this image is going to open, what this image is. So this is just a model I saw on the internet that runs image inferencing. Oh. Yeah, it seems like it resolved remote control cellular telephone handheld computer. So, oh, I forgot to say, like, I would like this to be an interactive session. If people have something, just shout it out. So let's go into the actual architecture of WASI Web GPU. So there are three sections that we want to talk about. One is the host side, how we make sure that the host is supported and the host gets all WASI Web GPU. Other side is the get side, and also how we get from the web spec into something that makes sense on WASI. The web spec is a little different. So let's start with the WIT generation. How do we get from the web GPU spec into actual WIT that's useful? So the web GPU, the actual web GPU spec is written in WebIDL, and we want to turn that into WIT. So the first thing is we built a tool called WebGPU to WIT. Just takes whatever WebIDL to WIT. That just takes arbitrary WebIDL, turns it into WIT, and that way we get a basic WIT. But that comes along with some assumptions that the web makes. like the DOM existing, like HTML element, Canvas, stuff like that, that we're not really bringing to the WASI. So that's why we built another tool called Wuyts Transforms, and it basically lets us do transforms on top of the Wuyts, remove all the cruft related to the web, add some things that make sense in WASI. Now, how do we get something from web GPU onto the actual screen? So because web GPU just runs on the actual GPU, but how do you get something that the output to run to show up on the screen? So on the web, you want something like a windowing system. You have the HTML canvas element, and the HTML canvas element can be connected to WebGL, WebGPU, some other graphics APIs. But for windowing systems, you only have the HTML canvas elements. We wanted WASI to be a little more flexible than that. So maybe different contexts, different windowing systems make sense. Maybe on embedded is different than desktop. So we try to decouple these. That's how you can see we have the web GPU. We're also working on WASI frame buffer, which is simple frame buffer API, CPU-based rendering. And there's probably going to be in the future some newer APIs that we'll want to bring to WASI, newer GPU APIs. On the left side, we have WASI Surface that we're working on, which is a very basic Surface API. Lets you do some pointer events, and keyboard events, but nothing too fancy. But in the future, someone will probably want a full windowing system, especially on desktop. You can do pretty powerful things. Someone will probably want that at some point, and we want to make sure that everything can come together nicely. So that's why we introduced the centerpiece, WASI graphics context, which is just an empty resource, and you can connect. All it can do is be connected to a graphics API on one side, a windowing system on the other side, and the host takes care of making sure that these things work together nicely. And you can use whatever windowing system you want, whatever graphics API you want. Any questions about that? Let's talk about the host for a second. So there are two parts for the host. One is how do we make sure that hosts are supported, that we provide a host and we're not just creating a spec, we're actually providing an implementation of this. And the other one is how do we get people to be able to try it? So the thing is, we put something called WASI GFX runtime, which is a plugin. For now, it's quite tied to Wasmtime, but you should be able to decouple it from Wasmtime. And it basically adds all the web GPU stuff to Wasmtime. So that you can, if you embed Wasmtime, you can embed WASI GFX runtime fairly easily. But most people that want to try WASI WebGPU probably don't want to play with that. So we provide already packages the GPU and Wasmtime so that you can play with it and try it with together with maybe WASI CLI, some existing code. Now, what about the guest? So on the guest side, you can obviously just write code against webgpu.wedge, and that should just work. It should be fairly easy. But what if you're coming from a language that already has support, already has a not standard, but commonly used WebGPU library? So in the Rust world, if you're writing WebGPU code, you would probably target WGPU. And WGPU has two backends. One is native and one runs in the browser, and automatically will detect whichever where you're running and get it to run according to the correct backend. It will select the correct backend. So we're working on a new backend for WGPU, a third backend. It's going to be for WASI, so that if you're compiling for WASI, it should automatically work. And that would bring most Rust UI libraries actually are backed by WGPU. So hopefully, once we have WASI backend for WGPU, we'll get all those UI libraries. In native world, we have WebGPU.h. It is used a lot in like C and C++, and we're working on a WASI implementation of that. So if you're targeting WebGPU.h, you're compiling to WASI, it just works. So we'll go into unanswered questions. Any questions, thoughts? All right. So we have a lot of unanswered questions, but I just wanted to give you a taste of a couple of them. And we would like input from the community here. So what do you think? The answer here. So the first one is, should WASI GFX part be broken into separate? So there's the WASI Web GPU, which is the main thing we're working on, but there's also WASI Surface, WASI Graphics Context, WASI Frame Buffer. Should these be separated into separate proposals? Should be one big proposal? Another one is, in Web GPU, there are methods that are like meant to be called at the end, last thing on a resource. So in Rust world, you would basically take ownership at one point. So the question is, should we, since WIT does have some sort of a ownership model, should we do something like that in WIT, or should we stick to what the web has done and just basically assume that users know not to use this resource after calling that end for that finish? And we'd like input on that. One more that I put on here is the WebIDL doesn't have any documentation generating the widgets from the WebIDL. So the question is, where's documentation coming from? One option is generating it from MDN, and there are already tools to do that. So we want part of the official spec. Please get involved. You can try it out at GraphTime. What's GFX GraphTime? You can check out the spec on the official WebAssembly org. You can contribute to projects we have now on the GitHub org, WASI GFX, and please join our meetings every Tuesday. We'd like more input from the community. That's it.
We have one request from chat, which is, can you share the slides on Zulip, please?
Make sure to do that right as I finish.
Yeah. Any other questions?
What's the scale of the size? I know nothing about graphics cards at all. Is this WebIDL like 15,000 WIT methods, or is it like 4?
I think close to it's a lot. It's a lot. It's more than 1,000 lines of WIT. I can open it right now. I'm able to.
Because a follow-up question that I would have is that you have these two different efforts. I'll focus just on the Rust side of things for now. So you have the WGPU crate hooking up to a WASI backend, and then you also have the WIT API being defined in Wasmtime, probably hooking up back to WGPU, but on the native backend. How much is that part all automated, or is that part mostly handwritten?
That is handwritten. Only the generation is automated. I don't think we can automate that. If you have a way to do that, that would be amazing.
There's still a significant amount of tools in there, so contributions welcome.
Oh yeah.
It runs most of the basic examples, but there's a long way, because there's a massive API footprint. There's a lot of methods that have to be subbed in. There's a lot of different options. You're translating between various enum types and strings, and just all this binding stuff. And there's a lot. Any other questions?
So what are the main performance concerns with this? Because like I tried doing a simple 2D. I used the frame buffer approach, admittedly, but if I wanted to copy a 2D image into the GPU, into a texture or something, that incurs an overhead, presumably going through WIT, where I can't use the same memory. It's got to be copied.
Yes, and we don't have an answer to that. a lot about this. We intentionally don't, we'll like obviously interact with like the people working on it, but we want to focus on WebGPU. Once someone figures out how to deal with memory sharing, we'll take that solution. For now, we're just literally copying, and we don't want that to be like the actual solution. We hope something better is coming.
To follow up on that, does the component model incur additional constraints over web GPUs already? So do you have to do more copies than a web GPU browser implementation would have to do?
Don't get frame buffers. Sorry, we don't get array buffers that we have on the web, and array buffers on the web can actually be backed by like GPU memory. We don't have that.
I asked some browser vendors at the moment, none of them actually use the UMA technique to allow zero copy between the guest content untrusted process and the raw GPU, because like that's a huge security thing. It could in theory be done with like a lot of hijinks, but nobody does at the moment. So there's always a copy. So the idea would be there's, in most of these cases, the easy, without much work, we can say the one copy that has to happen anyways is the one copy that happens from WIT out of the linear memory. The hard thing to do is say, how do we go all the way, turn it up to 11, and take advantage of Metal's UMA? Because apparently this is a thing in like some Apple silicon. And that one involves some trickier things because there's some actual real security concerns about raw GPU memory being persistently mapped. So do you flip to permissions, and how do you express that in a WASM friendly way that doesn't incur a bunch of like syscall overhead to flip permissions? But there's these great new chip features like MPK, and there's an ARM thing that's kind of like that lets you cheaply flip permissions, but how do we express that semantically in WASM? That's the interesting question to discuss. But again, this is only in UMA, which is mostly not what people are doing. Mostly there's a copy happening everywhere all the time because the graphics memory is way far away from and it's only in this like special app. I think it's the uncommon case. So I don't think we need to go straight all the way there. We should probably start with like, let's just have, let's get the non-UMA case optimal and then turn our sights on UMA is my intuition on that.
So that means basically taking it from 2 copies to 1 copy, which would largely match what happens in browser implementations
Yes.
today. But to be clear, with UMA, that's still a very active discussion of the web GPU work for the moment. Like, there's not something that the browsers themselves have 100% figured out yet.
Yeah, I don't think they've even figured this out. And they have more abilities because of these array buffers not being separable, and you have an indirection that they can disable them dynamically with the detachment feature of array buffers. So they even have extra advantage that we don't have, and they still haven't done it. So
Things there that on the spec level, we can do it. We're working on the spec, like how do we make sure that the spec allows it?
that is the interesting question.
The browser does it. So we have 2 copies right now to go from WebAssembly linear memory into a CPU local frame buffer from where it is copied into GPU local memory. And in the browser, you can directly operate on a single array buffer and then only have the 1 copy to the GPU. That's
Yes, the browser has, the name of the API is escaping me, but I mean, you can create your own memory pools. You can manage that process directly. There's a specific call in web GPU. I'll look it up and post in the chat that allows the browser to optimize that to push it directly into GPU memory. So yes, but we still have those 2 copies right now because it's just going to host side and host side to GPU.
we
In
might.
the browser is one case, and then there's outside of the browser but using WGPUs, and I think it's the latter case is easier.
Outside the browser.
Getting to messing with the browser's existing array buffer would probably force an extra copy, but of course they're open to adding additional web GPU APIs in the browser if we can show what the story is for WASM. And again, that's easier if we say, okay, there's still going to be a copy that happens from that CPU side memory into the GPU memory, but let's have that CPU side memory be linear memory. That's easier to do, I think, and there's a lot of good options there.
I was confused by Sean's comment about currently having 2 copies where browser native things only have to have 1 copy. It seems like we should also be able to get away with the 1 copy.
You should look. Okay.
I'm sure we see another cap.
Well, this would be a great birds of a feather hackathon session later today. So love to dig into it.
Anything else? Yeah.
You can grab it too.
So we are now free for lunch until 1:30.